We are here today for the talk by Xinmiao Zhang, that received his PhD in electrical engineering from the University of Minnesota. She's currently a professor at the Ohio State University. She was a senior technologist at Western Digital SanDisk from 2013-17. Prior to that, she was a Timothy E. and Alison Schroeder Associate Professor at CASS Western Reserve University. Professor Zhang's research spans the areas of VLSI architecture, design, digital storage and communications, cryptography, security, and signal processing. Professor Zhang is a recipient of the NSF Career Award 2009 and the College of Engineering Lumley Research Award at the Ohio State University in 2022. Professor Zhang is currently the VP for Technical Activities of IEEE Sequencing Systems Society and will be the Associate Editor-in-Chief of TCAS1 for 2024-2025. She is also served as on the organization of technical program committees of many conferences, including ISCAS, ICCC, GlobalCon, CIPS, Global CIP, Midwest, CASS, and the GLS VLSI. So thank you very much, Xinmiao, for accepting our invitation. And the floor is with you to start your talk.
Okay, thank you, Ricardo, for the introduction. It is my honor to give a talk here today. So today I'm going to talk about error correcting codes and the cryptography. Error correcting codes are used to ensure the reliability of numerous digital communication and storage systems. For example, they can be found in wireless and optical communications, magnetic storage, flash memories, and also distributed storage. Recently, they're also found in those biomedical implants. But even for these classic applications of error correcting codes, the next generation systems keeps bringing new requirements that demands the redesign of the decoder. For example, 5G or 6G wireless communications require decoder of much higher throughput, and the large-scale distributed storage system require codes that leads to much shorter latency in the failure recovery. Error correcting codes are also playing very important roles in the CHIPS Act of America, and as well as the similar programs in Europe, in Japan, and other countries. The chips can be divided into two categories, memory and those implementing logic functions. We need a memory of a higher bandwidth and a larger capacity in order to enable real-time machine learning, big data analytics, and many other new technology. And in order to achieve very high data access speed, we will need error correcting codes that achieve the same hyper-decoding throughput and at the same time good correction capability. These two requirements cannot be satisfied by any of the existing error correcting codes, and we need to develop new code as well as the corresponding high-speed decoder. Error correcting codes can be also utilized to handle the defect in those large-scale or wafer-scale integration. Let me see if I can have a pointer here. Ricardo, do you know if these two allow pointers? I guess not. Okay.
Sorry, it's okay.
Yeah, does it allow pointers? The PowerPoint has a laser pointer function available. Do you know if
May you try?
Yeah.
I'm not seeing the pointer.
Okay, that's fine. I will just go without a pointer then. And okay. So error correcting codes can be used to handle the defect in those large scale or wafer scale integration. And compared to have a duplicated function unit, error correcting codes will lead to much smaller overhead. And also in those larger scale chips, and we need heterogeneous interconnect such as a wireless or optical interconnect in order to resolve the routing congestion issue. However, at the same time, the transmission of those signals will consume high power that can potentially lead to heat dissipation issue. And the answer for all these problems will be the error correcting codes. By utilizing error correcting codes, the signal transmission power can be substantially reduced while you pay a little bit overhead for the implementation of the encoder and the decoder. Last but not least, error correcting codes are also the key enablers of quantum computing. But the quantum channel is fundamentally different from the wireless or storage channel we're familiar with. They have different error patterns, need different issues to be addressed. And as a result, we also need a new code and corresponding efficient hardware implementation of the decoder. Besides reliability, security is another very important aspect of many systems. So we have a cryptography scheme that can be utilized to protect the data during the transmission. However, the current public key ciphers, including RSA and elliptic curve cryptography, are no longer secure in the presence of quantum computers. Due to the fast development of quantum computing technology recently, we need a new cryptography scheme that resists quantum computing attack. And also, cloud computing is a very popular service now. So in this case, we not only need to consider protecting the data during the transmission, we also need to protect the data during the computation. However, existing cryptography scheme require that the decoding must be done first before any computation is possible. In this case, the cloud server will get access to the user data, and there's a privacy concern. In order to enable privacy-preserving cloud computing so that cloud server does not get access to any user data at all, we need a new cryptography scheme that allows the computation to be directly carried out on the ciphertext. And homomorphic encryption is one of such new technology. Security also has many layers. Besides protecting the data during the transmission, computing in system level, we also need to worry about hardware security. These days, the chip designers are sending their design to the third-party fabrication facility. In the case the foundry is untrustable, they may make extra chips and sell them for profit. And also, attacker can buy a chip from the market. By reverse engineering, they can recover the net list, and from there, they can also make counterfeit chips. These overproduced and counterfeit chips leads to billions of dollars revenue loss each year. And we need a new technique such as logic locking in order to protect these hardware chips and prevent chip counterfeiting. My research covered the broad area of VLSI architecture design, digital storage and communications, in particular error correcting codes, cryptography, hardware security, and signal processing. So a lot of those advanced algorithms involve complicated mathematical computations. If we map them directly to hardware implementation, it will often lead to overwhelming hardware complexity. In our design, instead of letting the algorithm decide the hardware implementation, we're feeding back the bottlenecks encountered during the hardware design to the algorithmic layer so that both the algorithm and the hardware implementation can be jointly optimized. Such a cross-layer integrated algorithmic and architectural optimizations can often lead to unprecedented improvement on the speed, silicon area, power consumption, and the chip-level security. In today's talk, I'm going to give you some summary of the recent topics we have been working on. These are the new topics that can potentially have a great impact on the next generation technology. In particular, I'm going to talk about error correcting codes enabling hyperspeed memory, next generation memory, locally recoverable eraser code that has much shorter latency for failure recovery in those large-scale distributed storage, a generalized logic locking scheme that can achieve better resilience towards different types of attack, as well as hardware accelerators for homomorphic encryption and post-quantum cryptography. First, let's look at error correcting codes for next generation memories. So the last 2 decades has witnessed much development on the memory technology. Now we have a solid-state drive based on flash memory. Their latency is much shorter compared to the traditional magnetic drive. On the other hand, their capacity is also approaching that of the magnetic drive. And such large and fast memory enable real-time machine learning, big data analytics, autonomous driving, and many other new technologies. In order to catch up with the next requirement of the next generation system, in order to further improve the data accessing speed to the next higher level, such as 1 terabyte per second, we can develop new type of memories, or we can also utilize a data-centric model. That is, instead of moving the data from the memory to the computation unit, we try to add some computation unit right next to the data, to the memory cell. This is because the memory cell themselves can achieve actually much higher bandwidth if we don't need to go through those protocols, interface, handshaking, where leveling, garbage collection, etc., to reach the output of the memory device. But those memory cells are naturally noisy. We have to carry out error correcting decoding before the data can be utilized for any computation or analytic. This means if we want to achieve hyperspeed access like a terabyte per second, we would need error correcting decoder to run also at the same very high decoding throughput. And on the other hand, we're also trying to increase the capacity of the memory. This means each of the memory cell is becoming smaller and the probability for error to happen is becoming much higher. As a result, those traditional error correcting codes used for DRAM, such as those single error correction and double error detecting code, is no longer sufficient. We need error correcting codes with much better correction capability. And these two requirements, hyperspeed decoding and the good correction capability combined together cannot be satisfied by any of the current error correcting codes utilized for memories. The current existing schemes such as LDPC code, Reed-Solomon, or BCH code are either too slow or their error correcting performance is quite limited. In order to address this issue, we can consider the newly developed generalized integrated interleaved code. The idea is that entire code word is divided into multiple short subcode words. Each of them is a classic Reed-Solomon or BCH code, depends on if you want to correct the simple errors or bit errors. So these codes are short, so the decoder can achieve very high throughput with low complexity. On the other hand, there are also nested code words. They belong to more powerful Reed-Solomon or BCH code. They are the linear combination of the subcode word. When their actual errors need to be corrected, we can utilize those nested code words to correct them. As a result, the GI code can also achieve much better error correcting performance compared to the individual subcode word. And here shows some simulation result. On the left-hand side is a longer code considered for flash memories. On the right-hand side is a shorter code that is targeting for those newer storage class memories. The black curve on the top, that is the decoding failure rate for the individual subcode word, and the color curve are the performance curve for the GI code. As you can see, the GI code can achieve orders of magnitude improvement on the error correcting performance, and the higher the level of nesting, the better the correcting performance. But still, we need to develop very high-speed decoders for this GI code. The GI decoding consists of two stages. First, we carry out the subword decoding over individual subcode word. They're just a classic Reed-Solomon or BCH decoding. We first compute the syndromes based on the received vector. Then we utilize the key equation solver, KES, and to find error locator polynomial from the syndrome. And the inverse root of those error locator polynomial will indicate the location of the errors, and they can be found by the exhaustive chain search. Only when their actual errors need to be corrected, we activate the second stage nested decoding. First, we utilize those nested syndrome to compute a higher order syndrome because they belong to those more powerful Reed-Solomon or BCH code, so we can compute more syndrome from them. And once we get more syndrome, we can compute a longer error locator polynomial. The polynomial of higher degree have more roots, and from there, we can correct more errors. And for both stages of decoding, the achievable clock frequency is limited by the KES step because it is an iterative process. In each iteration of the KES, I first calculate discrepancy coefficient. By utilizing the formula here, it will need a large multiplier and adder tree. And after that, it is multiplied with other polynomials to update error locator polynomial, so there's another multiplier in the data path. As a result, the critical paths become very long and delimit the achievable clock frequency of the decoder. And so the solution to this problem is to utilize a reformulated inversionless Bernoulli algorithm. It utilizes this discrepancy polynomial initialized according to the syndromes. And then this discrepancy polynomial is updated simultaneously with the error locator polynomial. It happens that one of the coefficient is the discrepancy coefficient needed for the next iteration. As a result, the computation overlaps and the critical path is only reduced to just one multiplier. And the critical path decides the minimum achievable clock period and accordingly the maximum achievable clock frequency. So this is what was done before for classic Reed-Solomon or BCH decoding, but the technique cannot be applied to the KES in the nested decoding. This is because those higher order syndromes are not available in the very beginning to initialize the discrepancy polynomial, and they're only calculated when the second stage nested decoding is activated. So in order to speed up the nested decoding, the KES in the nested decoding, we need to develop alternative reformulations of the KES. So the observation is that, okay, I guess there's one of the formula here is missing. when I convert it to this PDF. Okay, so when I have a higher order syndrome, the higher order syndrome can be utilized to update the discrepancy polynomial. But if I try to compute that updated discrepancy polynomial, I will end up with the formula here. And if I try to compute all these coefficients at the same time, I will end up with requiring multiplier and adder tree again. But fortunately, I don't need all these coefficients all at the same time. I just need one of them for each iteration. As you can see, each of the later coefficients actually involve one additional higher order syndrome for each of them. So from this, I can try to develop a nested KES algorithm that just incorporate one additional higher order syndrome for each iteration instead of all of them in the beginning. Based on this idea, we develop a reformulated nested KES algorithm whose critical path is reduced to 2 multiplier. But still, this is twice compared to the 1 multiplier for the classic resolvement or BCH decoding in the first stage of the GI decoding. The 2 multipliers are actually contributed by the 2 scalar here. If I truly want to reduce the critical path to just 1 multiplier, I want to compute the product of those scalars before they are utilized for the polynomial updating. So what I can do is to trace back the computations of those scalars, try to find out how they can be expressed in terms of values available in earlier iteration. And this will make the formula more complicated, but as long as I can start computation early, then I can break them down and only finish 1 multiplication in each clock cycle. In that case, the critical path will be reduced to 1 multiplier. So that is the idea we have, and we develop a fast nested KES algorithm to achieve this goal. And we also utilize the scaled version of the polynomials, and so that the number of multiplier required is reduced. So the best of the design we have derived so far is the last one. It requires less than 1/3 of the area compared to the design that reinitialize the discrepancy polynomial. And this is not shown up correctly. And at the same time, the number of clock cycles needed for design is the same as before, and the critical path is a little bit shorter. And for the shorter code considered for the storage class memory, our design can indeed achieve 1 terabyte per second throughput. Another bottleneck of the GI decoder design is low hardware utilization efficiency. This is because the nested decoding round has multiple rounds, and the later round has increasing correction capability. If we design a hardware unit to take care of the worst case, then many of them will be idling in the earlier decoding round. And in order to solve this problem, we came up with reconfigurable architecture for each of the design. As a result, the overall complexity of a GI decoder is reduced to 1/2. So that is about the coding scheme for next generation memories. Now let's take a look at the coding scheme for distributed storage. So a large-scale distributed storage is the backbone of numerous applications such as internet search, blockchain, and of course, cloud computing and others. Unfortunately, the storage node may fail, and so we need a failure recovery scheme. Many of the current distributed storage schemes are using eraser codes for failure recovery. Erasers basically are failures in coding terminology, and erasers are errors whose locations are known. So in the eraser coded scheme, we take one symbol from each of the data drive and then compute the parities according to a certain encoding algorithm. When there are failures, we utilize the other available symbol and go through a decoding process to recover those symbols. So the most popular eraser code used for this purpose are those maximum distance separable codes, such as the classic resolvement code. The reason is that they require the minimum amount of redundancy in order to recover from certain failures. For a code that encodes a K data symbol to an N symbol code word, it can correct any up to N-K erasers. So this is the minimum amount of redundancy needed. But the drawback of this MDS code is that they would require to access K data symbols for recovery, no matter how many failures there are, even if there's just one of them. For large-scale system, K may not be a small number. It can be 40 or 80 or even more than 100. Reading such a large number of symbols for failure recovery not only causes long latency, but more importantly, will cause large penalty on the network bandwidth. In order to be able to add more and more nodes to the system, in order to enable the continued scaling of distributed storage, we will need a failure recovery scheme that only requires to access a much smaller number of symbols. And this is possible when the number of erasers actually happen is less than the maximum correction capability. So the locally recoverable eraser code is a category of code that can be utilized to achieve this goal. These codes are typically not MDS, so we have a slightly higher redundancy. But by making utilize of those higher redundancy, the number of data drives need to be accessed to recover a small number of failures can be reduced to just a portion of what we had before. There are quite a few locally recoverable eraser code developed before, but different from the designs in coding for information theory society. Our design is not trying to develop a code that is bound achieving or that is optimal in certain information theoretical perspective. Instead, we want a code not only has a good locality, requires small number of symbols for recovery, but also at the same time is practical, can be applied to a lot of different systems. So that means I need a code that can support a wider range of possible code parameters, and I also want a code with a simple encoder. So we have a developed code based on parity splitting and also investigated eraser correcting GI code for achieving those goals. Our code based on parity splitting is a reinterpretation and extension of the famous Microsoft pyramid codes that is used in their Azure system. So now let's first take a look at that. So our code based on parity splitting started with an MDS code, and MDS code is linear block code. It means that it can be specified by a parity check matrix, and vector is a code word, and if and only if its product with the parity check matrix is equal to 0. So I see like when I convert my PowerPoint slides to the PDF, a lot of math symbols are actually gone. So you may, some of them are not showing up here, so I will try to explain them as much as possible. So in particular, I'm interested in the parity check matrix here. And this is not typically used to construct MDS code. The reason why I'm interested in such a parity check matrix because it helps to greatly reduce the complexity of the encoder and the decoder. So previous construction of the MDS code either use an identity padded with a Cauchy matrix instead of Vandermonde matrix, or the entire parity check matrix is a Vandermonde matrix. And however, if I want this code to be MDS, the requirement is that every square matrix of this H parity check matrix, including those consisting of non-consecutive rows and columns of this matrix, need to be invertible. And this requirement is not satisfied if I have too many rows, which equal to n minus k, the maximum correction capability, or too many columns here in the Vandermonde matrix, which is the code dimension. However, the number of symbols need to be corrected, or the number of erasers need to be corrected for the distributed storage system is typically quite small, such as 3 and 4. In this case, it can still allow reasonably large long enough code to be utilized, and at the same time, it's still MDS. So here in the parity check matrix, you see the symbol alpha. Alpha is a primitive element of the finite field. For those of you who are not familiar with the finite field, you can consider finite field GF2 to the Q as a set of the 2 to the Q elements with the corresponding addition and multiplication defined. Now let's take a look at example to see how the parity splitting and the code construction we have developed work. So here's example for the MDS code, and it has 4 different rows, and so that means it can correct any up to 4 erasers. And the total number of data symbols is equal to 12. So here, because I have a parity, I have identity matrix padded with Vandermonde matrix. So each of these parity can be computed as a linear combination of 12 data symbols. And in case there are failures, and the failures can be considered as a variable in those linear equations, and they can be recovered by solving the linear equation. But however, here, each of the parity is a linear combination of 12 data symbols. Therefore, in order to recover from any failure, I need to access 12 data symbols. That is what was happening before for the classic MDS code used traditionally for eraser correction. And now the idea is that I know this specify MDS code. So none of its square matrices is invertible. It's not invertible. So that means if I take a fewer rows, like 3 rows, fewer columns, like the 6 column like this, and pad it with another 3 by 3 identity, then none of its square matrices is not invertible either. And that means this will specify a code that can correct any up to 3 erasers in this data set, and that only require to access 6 data symbols instead of 12. So that is improvement of the locality by 50%. And similarly, I can group the other 6 data symbols into a group and pad it with another 3 by 3 identity. And any up to 3 erasers happen in that set of n can be also corrected by just accessing 6 instead of 12 symbols. And I don't have to stop here. I can keep dividing the data and split the parties. Every time I divide the data, I also don't need to divide them into sets of equal size. And I can divide the data in a very flexible way, depending on the probability of the erasers for each of the data drive, and also depending on the locality that I want to achieve. And so this is a very flexible scheme. It doesn't have much constraint on how the parities and how the data set should be split. And the best of all, this design can be implemented by very simple encoder and decoder. So for the encoder, because I have a vendor multi-matrix padded with identity, so each of the parity can be written as a linear combination of the data symbol here. And because of the vendor multi-matrix, I can apply the Horner's rule to rewrite it in a different formula like this. And this formula is translated to a simple feedback loop with just a constant multiplier and adder inside. When I have a split parities, I can still take out those common factors, and the rest of the part can still be rewritten by utilizing the Horner's rule, and the same multiplier and adder unit can be used to implement and compute the split parities. And when I need this scalar, when I need this parity, I will just multiply the scalar back during the decoding process. So remember, encoding is needed whenever I try to store the data into the memory, into the storage system, and the decoding is only needed when there are failures. So by multiplying the scalar back in the decoder instead of encoder, I have effectively shifted complexity from the encoder into the decoder, and accordingly reduced the overall system complexity. And for the decoder, similarly, I can recover the eraser by solving linear equations. And here I can try to come up with a formula for solving the set of linear equations. It turns out that because I have a vendor model matrix, so a lot of common terms got canceled out during the process of deriving these formulas, and I ended up with a 4 simplified formula like this. And this is much simpler compared to the previous construction of MDS code where the Cauchy matrix is utilized. If that is the case, if Cauchy matrix is utilized, each of the formula will have the same format as the most complicated one. So compared to the previous design, our non-traditional code construction also leads to great complexity reduction in the decoder implementation. When I have a split parities, I just need to multiply the scalar back and add it up the split parities, and that part only accounts for less than 15% of the overall decoder area. And we also have a look at eraser cracking codes, the locally recoverable eraser code implemented by using the GI code. So GI code is naturally locally recoverable because when the number of erasers happen small, they can be corrected by just accessing individual subword without referring to the others. However, when there are actual erasers need to be corrected, I need to utilize the nested code word. But the nested code word is a linear combination of every subcode word. In that case, every subwords need to be accessed. In order to further reduce the locality, so I don't need to access all the subcode word all the time, we develop a 3-layer GI code whose nesting matrix is in this format. So the subwords are divided into subgroups. When the number of actual erasers to be corrected is smaller, I will try to utilize those groups instead of all the subword for the correction. We also look at the 2-layer GI code and replace the lower triangular part of the nesting matrix by 0. A 0 means the corresponding subword is not involved in the nested code word specified by the rows. Whenever there are actual erasers to be corrected, I will try to utilize those nested code words involving a smaller number of subwords, and that will also help to further improve the decoding locality. So our main research goal is to simplify the hardware. However, there are still many of the storage systems using software to implement Reed-Solomon encoder and decoder for failure recovery. And Reed-Solomon codes are also the basic building component of many of the locally recoverable eraser code, as in the parity splitting code and the GI code I have just introduced. We found that the Reed-Solomon code is constructed over finite field. But there are so many different ways to construct a finite field of the same order. we can utilize the variation of the finite field to reduce the complexity of the corresponding constant multiplication involved. We can also apply the modified Reed-Muller transform to reduce the total number of constant multiplication involved. As a result, both the encoder and the decoder implementation in software can be speed up by a big portion. So that is about the coding scheme for failure recovery. Next, I want to talk a little bit about the logic locking. So for logic locking, we're trying to insert a key controlled function unit into the netlist so that the output of the circuit will become incorrect when the wrong key is utilized. And then this locked netlist will be sent to the foundry. In this case, even if there are counterfeit chips and overproduced chips, they are made by utilizing the locked netlist, so they would require a key in order to function correctly. And however, when the designer get the chip back from the foundry, they can send the chip together with the correct key to the authorized user so that the authorized user can utilize the chip. Those earlier logic locking schemes try to insert key-controlled gates such as XOR, XNOR multiplexer, and lookup tables in order to achieve this goal. But all of them can be easily compromised by the powerful satisfiability-based attack. So the set attack assumes that the attacker will have access to the netlist of the locked netlist. And that netlist describing the functionality of the circuit can be expressed in terms of a conjunctive normal form formula, the CASS formula. Besides that, the attacker also has access to activate the chip with the correctly entered bought from the open market. Then in the set attack, first the set solver can find a distinguishing input pattern, which is a basically input pattern that will lead to different outputs under different keys. So it is an input pattern that is able to tell some of the wrong key from the correct key. Then this input pattern is sent to the correct chip, to the activated chip to get the correct output. And then that correct output will be added as additional constraint to the CASS formula. And from there, a set of wrong key is excluded. And if we repeat this process until we can no longer find any distinguished input pattern, that means the remaining keys are correct, and we can pick any of them to be utilized as the correct key for the logic locking. In order to effectively resist the set attack, we need to insert a carefully designed logic locking block. For example, their anti-set design and the SARLOC design developed previously for resisting set attack. The idea of this is that for each of the input pattern, it will make the output wrong for only one wrong key. In that case, the set attack need to go through every input pattern in order to exclude all the wrong keys. So that means the number of iteration is 2 to the power of n, where n is number of input bit. So it's exponential with respect to the number of input bit. If we make the number of input bit large enough, then we can effectively resist the set attack. But the reason why these designs are resilient to the set attack also make them vulnerable to the approximate set, the F-set attack. The reason is that the probability of these designs, the probability of the wrong keys in this design are just 1. Here, the probability of a wrong key is defined as the number of input patterns leading to the wrong output. For the approximate set attack, is based on the set attack, but it does not go through all the iterations. It will just stop at the intermediate iteration after most of the wrong keys with high probability are excluded. And then here, if the probability is just 1, is the minimal probability. Then after it stops in the middle of the iteration, all the remaining keys will have a probability equal to 1. So if I just pick any of them and use them as the logic locking key, the output is still correct except for one of the input pattern, and that one specific input pattern may not happen. So most of the time, the circuit chip is still functioning. Another drawback of the previous design is that they may be vulnerable to the removal attack. So this is because many of them use the large AND or NAND tree for the implementation. But the output of such a large tree can be identified by calculating the signal skew from the netlist. Once I know the output of those large NAND and tree, then I can know the location of the signal. Then I can have the entire logic locking block removed, and from there, I will get netlist that no longer require any logic locking key. In order to achieve better resilience towards all kinds of different types of attack, we develop a generalized anti-set design. So one common feature shared by the previous design resilient to the set attack is that there's no overlap between the set of wrong keys that can be excluded by different distinguishing input pattern. So if I draw the input pattern and the wrong key in a two-dimensional array and denote the output, the wrong output by black square, then I will end up with a staircase pattern like this. But in our design, we would allow overlaps between the wrong key set. But we require that each of the wrong key set should have a unique wrong key that is not included in any of the other wrong key set. And then this unique wrong key will still guarantee that the number of iterations needed by the set attack is exponential. So we can still effectively resist the set attack. So those unique wrong key will correspond to the diagonal line here in this two-dimensional array. However, for the rest part of this two-dimensional array, I can have any pattern. I can have a higher probability. In that case, our design is more resilient to the F-set attack. And also because I have so many different possible patterns I can choose from, it is very difficult for the attacker to know exactly what is the feature he or she should be looking at in order to apply the removal attack. So our design is also much better at resisting the removal attack. And actually, many of the previous designs are special cases of our generalized anti-set design. So our design is better at resisting all type of attack. But here still, we're trying to utilize the output of this logic blocking block to flip a limited number of intermediate signals. We cannot use it to flip a large number of signals. In that case, if we just look for the signal with larger fan-out in the design, we will be able to locate the output here and have it removed. And I cannot utilize this to flip the output directly. Similarly, that is because in that case, I will know which is the output signal from the logic locking block and then have it removed. But there are also fault-tolerant functions, such as machine learning, approximate computing, or the low-density parity check error correcting codes. So those are fault-tolerating, which means even if I flip some of the intermediate signal, most likely the remaining computation are not affected, and the output is still correct. In that case, it means even if I pick just a random vector and utilize it as the wrong key, the intermediate signal got flipped, but the output is still correct. So in that case, the logic locking does not have any effect on the overall functionality of the chip at all, and the chip is not protected. It is very difficult to come up with logic locking that for general purpose circuit that can also protect these fault-tolerant functions. Instead, we should be exploring the specifics of these fault-tolerant functions in order to come up with effective logic locking approach. So here in particular, we have been considering the hardware accelerators for machine learning. And the observation is that many of the neural network will try to utilize the ReLU function. As you know, after the ReLU function, a lot of signal become zero. And therefore, many of the hardware accelerators are also using compression scheme for storing the feature maps. And so if it is zero, the feature map or the intermediate signal got discarded. If it is not zero, we try to store it in the memory in a compressed format. This compression is very important because the size of the memory needed for the neural network largely decides the latency and the performance of the neural network inference. And it needs a large amount of memory. But if the amount of memory we need to become too big, then the on-chip memory is no longer sufficient. We need to store the information on those off-chip memories. But the accessing of data from those off-chip memory costs much longer time and consume much higher power, and that will significantly degrade the latency of the neural network accelerator. So considering this, we came up with a logic locking scheme that try to utilize the compression part. So we have a match detector, which is responsible for telling if a signal is a zero. If it is zero, it should be discarded. If not, and then it should be sent to the compression block. So our design is that if the wrong key is utilized, then this match detector will label every feature map as non-zero. So it will go through the compression block and got stored in the memory system. So in that case, if a wrong key is utilized, the amount of the memory needed for the neural network inference will become much longer, and that will require much larger memory, and accordingly will require some off-chip memory and increase the latency of the neural network inference. Besides that, we also want to protect the neural network model itself because it will take a lot of effort to train the network. So what we do is to XOR a random vector to the biases of the neural network. And that XOR is compensated by the hardware adder here. And that actually also helps to achieve better resilience to the removal attack. So we cannot easily just remove this mesh detector and still have a functioning accelerator. And here shows some evaluation result of our design. So we look at the 3 popular neural network and try 3 different compression schemes. The yellow bar is the size of memory needed when the wrong key is entered. The green one is the size of the memory needed originally. As you can see, for many of the layers, the size of memory needed is increased by at least several times. That will substantially degrade the performance of the neural network when the wrong key is utilized. And also we found that even if there are some data we can utilize to retrain the network, because we have XOR the biases with random vector, the modified model and actually still have much lower accuracy compared to the original model, even if the retraining can be done a little bit. So our design can effectively protect both the hardware accelerator and the neural network model itself. The next topic I want to talk about is homomorphic encryption. So cloud computing, okay, so there's a part missing. This just says computation. So the cloud computing is gaining more and more popularity these days. This is because in that case, the user does not have to maintain expensive computing facility. They can just release the data to the cloud and have the computation done over there. So in the case that user data is sensitive and there's a privacy concerns, for example, and the application can be like involving the patient medical images used for magnetic diagnosis, or the data sent to the cloud server might be samples for genome sequencing, or it can be financial transaction data. In that case, we don't want the cloud server to get access to any of the user data. But if we use a traditional cryptography scheme, we have to carry out decryption before the computation is done. So in order to preserve the privacy of user data, to enable privacy-preserving cloud computing, we can utilize the new homomorphic encryption technique. It allows the computation to be directly carried out on the ciphertext, and the computation result here is still encrypted. And then after it's sent back to the user, and the user carry out the decryption, and it can recover the result of the cloud computing. So the most popular homomorphic encryption schemes, such as the BGV, BFV, and CKKS, which are named after the inventors, are based on the so-called ring learning with error problem. So in this system, each ciphertext consists of a pair of polynomials, and each polynomial is an element of this ring. The way the homomorphic encryption works is that random vectors are inserted during the encryption process in order to hide the secret messages. But the noise level grows with the computation, especially ciphertext multiplication. If the noise level becomes too high, then we can no longer recover the secret message after decryption. So once the noise reach a certain threshold, we need to utilize the bootstrapping process to reset noise level. But the bootstrapping is a quite expensive process. In order to reduce the frequency of activating the bootstrapping, we need to use very long polynomials, such as those with thousands of coefficients, and each coefficient also need to be big, such as having a couple of hundreds bit. And such a long polynomial with such large coefficient cause a lot of challenges in the high-speed implementation of homomorphic encryption. So we came up with quite a few techniques that can be utilized to simplify the individual building blocks of this homomorphic encryption. And due to the time limit, I will just talk about one of them. So, okay. Okay, so my figures are gone for some reason. Well, okay, I'll just talk about that. So we have a look at the decomposition, decomposed multiplication. So in decomposed multiplication, basically we are rewriting a long polynomial in terms of the segment. And then the multiplication of the long polynomials is expressed in terms of multiplication of the shorter segment. And in that case, we can utilize the Karasuba formula to rewrite the intermediate result in a different way so that the total number multiplication is reduced. But for the polynomials in the ring, there's always a modulus reduction after the long polynomial multiplication. Our design is that instead of waiting until the final product of the polynomial is derived and then applying the modulus reduction, we can incorporate the modulus reduction into each of the intermediate segment product. In that case, it will allow more intermediate result to be shared, and accordingly, that will be translated to a smaller number of memory blocks that are needed to store the intermediate result. So the memory contribute to the majority complexity of this decoder, and as a result, the overall to the majority complexity of the homomorphic encryption accelerator, and the result, overall complexity is also reduced. And the last topic I want to talk about is post-quantum cryptography. So there has been quite a lot of development on quantum computing technology. So the National Institute of Standards and Technology, the NIST, has been calling for proposals for post-quantum cryptography. There has been 4 rounds of evaluation so far, and for the finalists, they can be divided into 2 categories. And the first is those based on learning with error problem. It is quite similar to the homomorphic encryption and just involve different set of parameters. And the other are McLeod's crypto system based on the MDPC code. MDPC code is also linear block code, so that can be specified by the parity check matrix. In this system, we first generate a random parity check matrix that will be the secret key. And then we compute the generator matrix from the parity matrix that will be the public key. The encryption process is basically to multiply the message vector with the generator matrix. For here, we have a code word of the MDPC code. Then it is added up with a vector of certain weight, and this can be considered as error vector added to the code word. In the decryption process, we basically carry out the decoding. If the vector added is decodable error pattern, then we'll be able to recover the secret message. So you might have heard of LDPC code before, the low density parity check code. It is one of the most broadly used error correcting codes for digital storage and communications. For example, you can find them in magnetic drive, flash memory, digital video broadcasting, and also optical communication. But this code and the decoding algorithm and the encoder implementation have been extensively studied. However, the simplification for the decoder cannot be directly extended for the MDPC code because of the fundamentally different structure in the parity check matrix. For LDPC code, it consists of a large number of smaller cyclically shifted identity matrix. Here, the diagonal rows indicate the location of the non-zeros. Because each submatrix only have 1 non-zero entry in each row, each column, so we can use a very simple check node unit and the variable node unit to implement the decoder. But for the MDPC code, the parity check matrix involve a very large but very few submatrices. And also for each of the submatrices, although it's a cyclically shifted matrices, but the location of those ones are random. And as a result, because of the large dimension, I cannot possibly process 1 submatrix each time for parallel processing. And if I try to divide them into smaller square matrices, then they have multiple non-zero entries in each row and each column. That will lead to much higher complexity in the decoder. And the number of ones vary between the submatrices. And in that case, that means a lot of hardware units will be idling in most of the time. So for MDPC code, we need to look for alternative strategies for the parallel processing. So the previous design, okay, the animation is gone. So the previous design, we're processing 1 column at a time. So because the matrices are cyclically shifted, so I don't need to store all the information of the entire parity check matrix. I can just store 1 column and try to divide the next column by cyclical shift. But still, 1 column is quite big. It has thousands of bits. So instead, I want to process a segment of error bit each time. And in that case, I will just finish the segment 1 by 1 in the first column and move on to the next. But here, the cheapo speed up can be achieved by this design is quite limited. It is because the medium density parity check, the medium is relatively speaking. Still, many of the error bit segment is still all 0 if L is not big number, such as 32. So considering that we are not going to process each of the error segment, we will only store those the non-zero error bit segment as well as the corresponding indices and only process them. This not only reduces the size of memory needed for storing the information about the parity check matrix, but also leads to substantial reduction on the latency. And also we are processing column I plus L after column I. This is because the non-zero segment in column I plus L are exactly the same as in column I except the one on the edge. In this case, I don't need to even update the memory for storing those error bit segments. I just need to update the indices and add 1 to them. And this helps to substantially reduce the memory access and corresponding power consumption. But still, achievable speed up is not exactly L, even if you want to process L bit segment. This is because in each of the segment, there's typically still only 1 or 2 non-zero bit. In order to substantially improve the processing speed, we need to add constraint to the parity check matrix construction. Here, in order to achieve error parallel design, the constraint we need to add is that the adjacent pair of ones, the distance should be at least L. And then because each of the row is a cyclically shifted version of the previous row, so we just need to add a constraint to the first row. And the same constraint will be maintained for the other row. So previous construction is totally random. Now we have additional constraint for the purpose of enable efficient parallel processing. We need to evaluate how this constraint will affect the decoding performance as well as the triple level security. And we found that if the parallelism is not very high, such as up to 32, actually there's no noticeable decoding failure degradation observed associated with this additional constraint. And the total number of usable key has been reduced, but still after reduction, there are 2 to the power of 6 or 700, that many different number of keys, and still that is more than enough for most of the practical system. And one of the most powerful attack to the MDPC code, the McLeese system based on the MDPC code is called the reaction attack. It tries to utilize the decoding failure to recover the structure of the secret parity check matrix. And the number of decoding trials needed in that attack is decided by the decoding failure as well as the possible spectrum of the parity check matrix. And our proposed scheme does not degrade error correcting performance, and the possible range of the spectrum of like the distance between the pair of ones is just reduced a little bit. So overall, we only observe negligible degradation on the number of decoding trials needed by the attack. But still, we can divide H matrix in different way to truly achieve L times the speed up for error parallel processing. So the most straightforward way to divide H parity check matrix is to divide them into block rows and columns according to fixed indices like this. But in this case, those non-zero submatrices still may not have exactly L non-zero entries. For example, the one here only have one non-zero entry, and the one here only have a small 3 non-zero entry. So because of that, the effective speed up compared to the zero design is far less than L, which is typically actually between 60 to 70% of the parallelism. So what we can do is to divide the parity check matrix in different way. We will try to put the non-zero entries in those identity submatrices. So in that case, we divide the block rows and the columns according to with different indices, not according to the fixed indices. So this division can still be implemented with low complexity overhead. So the observation is that here, the ones in the top left corner may not start in a position that is aligned with the blocks of columns and rows. So this is for parallel processing. I'm going to store the messages for column 0 to 3 in one address and 4 to 7 in another address and 8 to 12 in address 3. So this is not perfect aligned with the memory, with the information storage on memory. However, the messages belonging to one square matrix, they can be always extracted by the adjacent to memory location. So considering that, if we just divide the memory into even and odd blocks, and we will be always able to get all the information we needed in the same clock cycle. And if we utilize this idea, because each of the square matrices is a perfect identity, so we can effectively achieve L times the speed up compared to the zero design if we're processing an L by L block at a time. So in summary, error correcting codes and cryptography are essential to many systems. And although they have been active topic for research for more than half a decade, but still those new applications and next generation technologies keep bringing new requirements. It might be higher throughput requirement and better error correcting capability, or just a different code parameter. Whenever any of this change, it requires a new design and bring many challenges to both the code and code design and encoder implementation. And we cannot just rely on the development of VRSI technology to solve this problem. It helps to speed up the computation unit, but amount of speed up that can be achieved is limited. Instead, we should be looking at algorithmic reformulations to substantially reduce the number of computation that is needed. And the same technique will also apply to other advanced algorithms, not limited to the error correcting coding and the cryptography scheme. And I look forward to expand my research to other topics and develop practical and highly efficient implementation for those advanced algorithms so that they can be broadly applied in practical systems. Okay, so that is the end of my presentation. So for some reason, a lot of figures and equations are not shown up correctly, and I hope I have explained some of this idea clearly. Thank you.
Thank you very much, Xinmiao. So time for questions. I'm seeing no question yet in the chat channel. So if you have a question, please do it as soon as possible. Here also in the audience, any question?
Yes, I have.
Can you go here? So there is a question by Professor Jarbas.
Hello, Professor Xinmiao. Thank you for your presentation. I have heard in slides about GNN, deep neural networks are naturally fault-tolerant, prepared for that. But I have done some experiment that in specific part of the neural network, if you have some errors like bit flip, we can have serious problems about that. I'd like to see if you can explain about that.
Well, of course, there are some signal that is more critical compared to the others in the neural network. So that might be a better place to flip the signal. However, we need to assume the user also, the attacker also know that information. So the attacker has the netlist. So the netlist, from the netlist, the attacker can recover the functionality of every logic block in that circuit chip. So if the attacker also has information about which signal is more critical so that they should be flipped, then they can possibly look at those signals and try to identify the corresponding output of the logic locking block. And that can be also another type of removal attack. So here, it's still very difficult to come up with a like logic locking scheme targeting for general purpose circuit, and that can also effectively protect those fault-tolerant functions at the same time. So instead, we should be looking at the algorithmic features and try to exploit the specifics of those fault-tolerant functions in order to better protect them. So what I show today is a machine learning hardware accelerator. We have also done some work for the low-density parity check decoder. And for that decoder, similarly, and there are maybe it is even worse or even more difficult to protect compared to the neural network. We found that even the most critical signal, like the sign bit and the most significant bit of the magnitude of the messages, even if we flip them, and the decoder output is still correct most of the time. So what we have done is to try to lock the stop function checking that block in order to protect the chip. So it depends. I really think it depends on the specific algorithm you want to protect in those fault-tolerant functions.
So thank you very much. Another question from the audience here. No? So I see no questions also here in the chat channel, but so I have one. As you also state in the conclusions, so the algorithm reformulation enables significant complexity reduction and hardware performance improvements also. So the complexity reduction should also means power reduction. No? So do you have some measurement about the level of power reduction you can get with this?
We didn't measure the power consumption directly, but in general, the algorithmic reformulation helped to reduce the number, for example, multiplications. After the reduction, the multiplication is multipliers carry out different computations, but it do not necessarily carry like computations which has a much higher power consumption compared to each of the individual multiplier we had before. So in general, by reducing the total number of computation unit, we can reduce the power consumption as well. And also in our design, we typically don't want a hardware unit that is idling for some time. So we are trying to make each of the hardware unit active and busy in each of the clock cycle. So in that case, the number of hardware unit is a really good indication about the relative power consumption.
Okay, thank you. I'm seeing no more questions here, neither in the chat channel. So dear Xinmiao, so thank you very much for your talk. So it was great, a very interesting subject. And it was a coincidence here that Professor Jarvis also worked in some related topics. No? So thank you very much, and I hope to see you soon in person in the next CASS event. So
Yeah,
thank
thank you for
you.
inviting me again, and I hope you enjoy the holidays. And I hope there will be also opportunities that can collaborate with you on some of these topics.
Thank you. So bye-bye.
Bye.
See you soon.
See you.
Bye.